So as announced, Dr. Koppelmann will give us an introduction into GPU programming. He is the one who can do that best, because I have no idea what GPUs are compared to him. That's why I asked him to do that. So thank you, David, for doing that.
No problem.
Please go ahead.
All right, so I thought I'd like to talk about, to start this off, we're going to get into CUDA, but first I wanted to talk about the differences between CPUs, which I'm assuming you're familiar with, and GPUs. So they are different in very significant ways, and these differences impact how they are programmed. So I'm going to start by comparing them with some numbers, and that will bring out one of the biggest important differences, and that is the massive parallelism that's required to make use of them. There's also this other issue of having what I like to call a Baroque memory system. Okay, so first, the definition of a GPU is graphics processing unit, which describes their origin. So they started off being meant for accelerating 3D graphics. So when you design a GPU, one of the goals here is to maximize the operation throughput on a chip, in particular floating point throughput. So cover as much of a chip as you can with floating point units. So basically they're trying to maximize the floating point units per area. Doing so, though, while still being able to compute their workload. Clearly, if you have floating point units that don't have operands, they're useless. So what you need to be able to do is deliver operands to these floating point units, and of course take the results and send them where they need to go. Okay, so that's been one of the design goals of GPUs since the beginning, but of course with a target workload. So they were originally designed, as I said, for 3D graphics. So once upon a time, when you did graphics on a computer, there was a frame buffer that the CPU wrote, and some other device would read that and send it to your monitor. Okay, but for graphics, you wanted little special effects. At first, they called them sprites, a little image that you wanted to move, or you wanted to do copies. But these were fairly simple things that could be done, sometimes with very simple specialized hardware like DMA. What really took computation was 3D graphics. Because in 3D graphics, you have this imaginary world that you represent using coordinates in a three-dimensional space. I say imaginary, but if it's something like a flight simulator, that could be a real world, or at least a copy of real world that you want to fly in. But the point here is representation of the world is made up by a computer and consists of coordinates in three-dimensional space describing primitives, usually triangles. And what the GPU had to do, or the graphics system had to do, is to take that triangle in three-dimensional space, project it onto a screen, so the coordinates were now pixel coordinates, and then fill in the triangles. So to do that, one needs to do matrix multiplications. One needs to take the coordinates in an arbitrary three-dimensional space and apply a coordinate transformation that will project them onto that two-dimensional space, sometimes done using multiple steps. So for that, this was in the 80s, this chip called the Silicon Graphics Engine. I don't know if I have it here. That was designed for that. So basically, this would do a 4x4 matrix multiply, and you could have several of these chips chained together. These were used at the time for engineering workstations, and they might have been used in like flight simulators of, when I say flight simulator, I don't mean the game that you buy from Microsoft. I'm talking about something used to train pilots, even military pilots. Okay. But these also were adopted for home computers, which had a much larger market. Okay, and that's significant because you get economies of scale. So when they were adopted to the home market, there was large economies of scale, so you could put more engineering into it. So I said that you took a triangle in arbitrary three-dimensional space, projected onto a screen. That's fairly straightforward. What takes more effort is doing lighting calculations and putting textures on. And so for lighting calculations initially, they did simplifications of a physically derived lighting mechanism. In no way could they do ray tracing back then. But even getting colors right was an approximation. People who designed graphics, perhaps for military flight simulators, maybe for home use for games, they were interested in aesthetics. And so whatever built-in lighting that came with this graphic system may not have been suitable for them. The colors just didn't seem right. The material that was supposed to be cloth or clay or metal didn't quite look right. So graphic systems then said, well, we can't just have a few built-in lighting models, because look at all the people who are trying to use this. There's no way that we could make one system that would satisfy all of their demands, since they're so varied. So let's make it programmable. Okay, so this programmability would let someone then, a game designer or someone doing a military flight simulator or whatever, play with the lighting to get the effect that they wanted. This was also done for textures. So textures are kind of like wallpaper that you put on objects. They also challenge the system, and programmability there was also used with textures in the sense that you would take a texture that would describe how an object looked, another texture which described how rough it was, combine it in some way. This also was helped a lot by programmability. So these things became programmable. But because they were sold to consumers in the expansion cards for home computers as they grew, and video game consoles, there were large economies of scale. So making these things programmable, they could afford the engineering, but also these things were relatively inexpensive. But still initially, these things were designed for graphics. Now, I don't remember the name, but at some point, someone looked at these things, and these were games that they had at home, and did a rough calculation of how much calculation they were doing. And they realized that this is a fairly powerful computer. You know, I mean, this compares very favorably to what I have at the lab at work, and it's a hell of a lot cheaper. What if I could program it? Well, I said that these things were programmable to do things like lighting calculations and textures, but ultimately what you did is the output of that calculation wrote a frame buffer. And when you wrote the frame buffer, you wrote integers. So this person, and I'm not quite sure if this was an act of procrastination or serious research, but actually tried to formulate a scientific calculation as a fragment shader, and its outputs would be integers. Okay? The input to this data would be related to coordinates and colors. Outputs would be integers. But although it did write a frame buffer, there are ways of copying the frame buffer back into the host CPU. And they would take that data and then convert it back into floating point. And they found that, you know, this actually is fast and it can work. Okay, now it sounds like a novelty. So first of all, the programming that thing was no doubt a pain in the neck. Even by standards of GPU programming today, because you were fighting the thing. You know, scaled integers where you'd rather use floating point and so forth. So I guess NVIDIA found out what was going on, and I think when they found out what was going on, they were in a good mood. Why do I say that? Well, if you work with CPUs and you want information about how to program it, no problem. Intel, AMD, they'll give you tons of information, okay? Details on the instruction set, of course, assemblers, and if you want to do your own assembler or compiler or whatever, they will provide all the support you need. But GPUs were different, and the reason that they were different is because in order to do all of this, remember the lighting calculations, the projection, these were done by libraries, closed libraries. The inputs would be these device-independent languages like OpenGL or DirectX. Okay, but these were high-level languages which a driver would compile down to the actual language internally. Now, these shaders were programmed for very specific devices, and they wouldn't describe the internal architecture. So the culture for these graphics processors was much more closed. So I said NVIDIA was in a good mood. I imagine there was an argument, and they said, well, what we really should do is sue these people into poverty because they have reverse engineered our system and stolen our trade secrets. Fortunately, that wasn't the view that prevailed. The other view was, well, hey, if they want to use these chips in that way, why don't we help them? And that is what they did. They said, all right, obviously trying to program this using a fragment shader is really, really difficult. We'll make our own language to program them. And they called it CUDA, and I still don't remember what CUDA stands for. And needless to say, the rest is history. That started with about the 8800 GPU. And so it's a method of programming GPU chips where the goal is not to write a frame buffer to show a frame from a simulated 3D world, but just to do a calculation. Now, at this point, CUDA can write a frame buffer if you want, but it's not really meant for graphics. Okay, so that's so GPUs are everywhere. You probably have them in the phone and so forth. And I don't need to tell you this stuff. All right, so the examples, all right, the 5090, that's the latest consumer one. Does anyone have one yet? Who has one? Okay, you don't have to say, I mean, yeah, if you raise your hand, obviously people are going to want to play with it, so you don't have to. The data center level chip, Blackwell B100, NVIDIA just announced new chips, Feynman, and a few others. You know, scant details, although the details just show scaling, but there's probably more to it, more memory. NVIDIA is not the only game in town, Radeon. These are GPU chips. When you talk about computational accelerators, there are plenty more manufacturers, but I'm sticking to GPUs. But there are computational accelerators that are meant for machine learning, and I'm not going to discuss these right here. Well, I could, but that's not what I'm supposed to. All right, so I said I was going to compare the CPU to the GPU, and I'm comparing this so that you could see what the differences are and why some of those differences impact programming. So what are we comparing? So here are my two sample devices. These are roughly comparable. An Intel Xeon Silver 4316 GPU and NVIDIA GeForce RTX 4090. So they are roughly at about the same point in time. And another advantage is they're available in the ECE student laboratory. So if you want, you can come and play with them. Now, you might wonder, why am I comparing a data center grade, what do they call these? A CPU. It's not server, it's something else. That's the word for this. With something which is meant for the consumer grade. But if you look at the data center equivalent, the H100, in some ways that RTX is superior. So we have both here. And I've used both, but a lot of times the 4090 is faster. Okay, one reason is I'm not doing double precision calculations. So if you're not using double precision floating point and you don't need a massive amount of memory, the 4090s are the way to go. And of course the price helps too. All right, so let's compare them. So first way to compare them is floating point and floating point bandwidth. So when I use the term bandwidth, I'm talking about the peak rate of something. So operations per unit time. So for floating point bandwidth, the operation is going to be a fused multiply add operation. And for this comparison, we're going to look at single precision, the IEEE 754 single precision. So the operation is a multiply add, which is a basic operation in scientific computing, graphics, machine learning. So it's used very widely. Just a word of warning, when other people quote these numbers, they count that as 2 operations. But because their implementation is invariably fused together, I'm counting it as 1. All right, the time unit here, it's another thing which is a little different. I'm going to use cycles partly because it's easier to, it's closer to the hardware. Also, it doesn't really matter because the clock frequency of those 2 devices, if you noticed, are about the same. Also, clock frequency nowadays is a harder thing to pin down. It used to be when you got a chip and it said, and if it was a 500 megahertz clock, the clock ran at 500 megahertz period. As we probably know, clock frequencies nowadays move up and down. Okay, so if you're in a low power mode, it's going to throttle down. If, on the other hand, it looks like there's a lot of work to do, it's going to overclock itself. It's going to computationally sprint. So as long as it's not overheating, it'll be above the rated amount. So if you actually look at calculations, a lot of times those clock frequencies go up and down. All right. So here, for this comparison, it's per cycle. And if you look at the rated clock frequencies of the 2 devices, are about the same. All right, so for the Xeon, floating point bandwidth, here's a calculation. First of all, it has 20 cores. Each core has 2 vector units. And the vector units will have 16 lanes for single precision. So it's AVX 512. That's 512 bits. So the single precision is 32 bits, 512 over 32 is 16. All right, so here, 20 times 2 times 16 is 640 floating point operations per clock cycle. Okay, if you want per second, then it's about 3 gigahertz, 2 to 3 gigahertz. This is, those things will run at 3.8 gigahertz if you let them, although the rated clock frequency is 2 point something. So a rough number, just multiply that by 3 billion. Okay, so then you'll have 600, well, about 1.8 teraflops. All right, what about the GPU? So here, the equivalent of a core in a GPU is a symmetric multiprocessor, SM, and there are 128 of them. Each of these has 128 FP32 units. And FP32 can sustain a bandwidth of 1 multiply add per clock cycle. So multiplying those 2 numbers, you get 16,384 floating point operations per clock cycle. By the way, I am not taking into account the tensor processors. So there are tensor cores in the GPUs. So I'm not taking them into account. If I did, you'd multiply by 4, but there'd be an asterisk. And the asterisk is you'd have to do it at a lower precision. So those values you multiply would have to be 16 bits. You'd accumulate into 32. So here, the comparison is fair. But just in case anyone might feel offended, this ignores the tensor cores. All right, so what we have is about 25 times higher floating point bandwidth. Okay, now how is this achieved? And it's not that the NVIDIA engineers are smarter or anything. It's just they have different priorities. So if you look at a CPU, there's 2 ways of describing how a CPU is designed depending upon how charitable you are. So the less charitable way, it's designed for programmers who are not sure where they're going and they're not sure what they need. Okay? But that doesn't sound good. I think a better way is it's like a sports car. You could make sharp turns and speed through, slaloms and stuff like that. That sounds better. But what exactly am I talking about? When I talk about these turns, I'm talking about the thread of control to a program. There's a branch in the code. You have if statements. You have loops where you need to test the exit condition. These ultimately compile down to branch instructions. And because computation at CPUs is heavily overlapped, by the time you resolve or figure out if a branch is taken, you've already partially operated on multiple instructions after the branch. So for that to be effective, how do you know whether the branch is taken or not. You must know that in order to get these instructions. And the answer is probably no, is the branch is predicted. So there's a lot of hardware in there, first to predict the branch, but also to clean up the mess. Okay, there are other issues too that CPUs take care of, and that is sometimes when you have an instruction, the operands are not yet ready. This particularly happens if you have a load instruction. It might miss the L1 cache, hit L2. So there's going to be a delay. In a simple processor, where it's called statically scheduled, the instructions that are waiting for that operand are going to, well, basically everything after that load instruction is going to stall. So the whole thing is going to be held up. In dynamically scheduled CPUs, which includes most of what you have, it's in your pocket, it's in my laptop, instead what happens is the load and the instructions that depend upon it wait around, but other instructions proceed. So it's referred to as dynamic scheduling, and it allows instructions to execute when their operands become ready, as opposed to executing in program order. Executing in program order is easy and it's always correct, but doing so will cause the system to stall when one instruction does not finish fast enough. Okay, that does not come cheap. Somewhere in these slides, if you're in the mood, I could show you a diagram of a dynamically scheduled system. So, as you probably guess, GPUs lack this dynamic scheduling. The threads of control go sequentially, and if there is prediction, there probably is not prediction in these things. Okay, another thing that CPUs do that GPUs don't is with the number of instructions that can execute at a time. So you may have heard the term superscalar. So in a typical CPU, like an Intel CPU, you might be able to execute at, well, I guess a peak would be around 8 instructions at a time. Now, it's more complicated, they're micro-ops, but roughly 8 instructions at a time peak. This is from the same thread of control. That also takes a lot of hardware. So you can have, I didn't explain this, but you could have over 100 different instructions from a thread of control in flight. The scheduler needs to figure out which one to execute, and it can start around 8 per cycle if it could find them. That takes a lot of energy, a lot of space, a lot of engineering. GPUs lack all of that. And so there is more room for these floating point units. Okay? All right, now off-chip data bandwidth. So here the units are fairly simple. It's bytes per second or bytes per unit time. So for the Xeon, this is based upon measurement, about 38 gigabytes per second off-chip. RTX 4090, well, the API reports about 1 terabyte per second. Micro benchmarks pretty close. So here we could see again about 25 times higher. Now, how is that accomplished? And here the GPUs do something the CPUs don't. So to communicate off-chip, you need to connect wires to the chip. The conventional way of doing so is, here's a chip. You have bonding pads here, and these are physical wires. This is a package. I don't know if you can see it here. So this is a little pin. This whole thing is a chip package. This is a chip. And there's a whole bunch of pins down here. They used to be along the side, but the current configuration is a bed of nails. But the key here, this is the chip. They were around the periphery. And these are fairly large. So here we're on a chip. These might be thin wires, but this has to be a heavy pin to be pressed into the socket, goes into the circuit board. It finds its way to a glue chip, then the memory modules. So there are several problems here. First of all, there's going to be a certain limit to the perimeter of this thing. Also, to drive this, you need to put electric charge in here. And the larger something is, the more electric charge you need to either put in or take out to get the voltage transition that's detectable. Okay, so I know you're computer science, so most of you. So you've heard of the speed of light, of course, but electrical signals in electronic devices do not travel at the speed of light. They are limited by the capacitance of the device. They don't travel as waves. So that's going to slow it down. So there's two issues here. The fact that you're dealing with the perimeter and that you have to charge it. So what the NVIDIA GPUs have done in the past few years is, rather than connecting the memory in this conventional way, the chips themselves are stacked. So we kind of, so this is a side view. So the side view of the GPU chip, and you have DRAM chips that are stacked on top. So rather than having these pads around the periphery, you have these things all around the chip like this. And when you stack one chip on another, they make contact. Okay, so this part here is collectively called high bandwidth memory. Now, the advantage is you could have a lot more pins, so you get much higher bandwidth, and we could see it here. There is a downside, and that is, you know, when you buy a computer and you say, oh, I don't have enough memory to do my models, you know, I want to run the 70 gigabyte model, and there's not enough memory to do it. So what do? You just upgrade the DRAM in your computer, right? Can't do it here. The only choice is to buy a whole new system. Okay, so here the DRAM is far less upgradable. It's basically on top of the chip. But the advantage is you get this much, much higher bandwidth. Now, you'll notice, I don't know if I mentioned it yet, it's also 25 times. Is that a coincidence? And probably not. Why are both of them 25%? And it has to do with something called computational intensity. I don't know if you've spoken about it. Okay, so right, so you want to keep the computational intensity balanced. In other words, how many floating point operations do you need to do for each data element that crosses the off-chip boundary? Okay, now that number depends upon the nature of the computation that you're doing and also the skill of the programmer in making use of the cache. So programmers maybe are not going to be so much better on, so those problems don't really change. So they're roughly the same, about 25 times in the computational intensity. I think it's on the next slide, about 100 something. Do I have it here? Oh, no, 65. So here, if we measure this in the units of floating point bandwidth over data bandwidth, we get 65, but the units here are going to be floating point operations per element. So it's not per byte, you know, so that we have something meaningful. So with that 65 number, it means if you want to perfectly balance off-chip data bandwidth and communications, then you need to find a way of doing 65 floating point operations for each unit of data that's transferred, each element, which I should point out is not an easy thing. Okay, depending upon what you're doing. Now, there are some, of course, calculations that are inherently bandwidth limited. There are others, like matrix multiplications, where you could easily get it to be floating point bound. I say easily in principle, but still, it does require some skill. All right. Now, right, so far, it seems that these things are similar. Just so GPUs have beefed up floating point, beefed up data bandwidth. For data bandwidth, that's easy. They just stack the chips on top. CPUs could have done that. They would have lost expandability. Floating point is different. With floating point, to actually achieve that, they had to dispense with dynamic scheduling and branch prediction, and wide superscalar issue. Okay, so when you dispense with that, what other changes are there? And one very, very significant difference, and this is going to affect programming the devices, are the number of threads of control. Now, of course, parallel programming class, I don't have to define threads of control. I just want to compare the numbers. Slides here need a little formatting. So the minimum number of threads of control. For the Xeon 20, why? It's a 20-core chip, 1 thread per core. Yeah, I know you could launch more cores, but you could launch more threads. But here, when we talk about threads of control, we want the thread to be active in doing computation work, not sitting in a queue somewhere or being scheduled out. What about the 4090? Now here it becomes a little, well, first of all, there are 128 symmetric multiprocessors. And the minimum to have any chance of saturating the device is 128. So 16,384 threads of control. Now, when I say thread of control, the way to think about it is a burden on the programmer, because you need to take that parallel algorithm and find work for all of those threads in such a way that you get speed up. Okay? So if your algorithm doesn't scale well, where you increase the number of threads and the efficiency goes down, the GPU is definitely not for you. Okay, so here, 800 times more threads. And so this is the minimum in the sense that if you have fewer than this number of threads, you are going to be leaving some of the hardware idle. Okay, what about a maximum? Well, for the Xeon, it's not that different. The Xeon has something called hyperthreading. What that means is you can have 2 thread contexts on a core simultaneously, and the scheduler will pick one context or the other. So it's essentially a 0 overhead context switch. In fact, it's not a context switch in the software sense, where you need to copy out the old registers and copy in the new registers. It's simply a decision on which context to fetch an instruction for. But once fetched, the instructions intermingle the 2 contexts. They operate together. They're in flight together. They share resources and so forth. Of course, they're different threads. They have different register sets. But they're side by side. Okay? So that's how it works in hyperthreading. Well, what about, so the maximum number is 40, just twice as much. What about for the GPU? Well, there are 128 SMs. The maximum, now the way that threads are measured in GPUs is sometimes done in warps. So 32 is the number of threads in a warp, and the maximum number of warps per SM on the 4090 is 48. If it were in H100, it would be 64. So it's higher, but not a lot higher. So that works out to 196,608 threads. So that's almost 5,000 times more. Okay, now NVIDIA did not put all of those contexts in just to have a big number on their marketing materials. It's there because sometimes you do need to use it. So the burden in parallel programming is immensely higher on GPUs. Okay, let's see what I have here next. All right, so I didn't have time to format this, but another big difference is in cache. So here, a quick look at the cache. On the Xeon, the level 1 data cache, it's 48 KB, and that's per core, 960 total. Level 2, and this is local to a core, 1.2 MB, the total for the chip, 25.6. And the level 3, which is also on chip, and this is shared, 30 MB. Okay, I'll get into this in a moment. On the GPU, 100 KB of L1, so 1280 for the chip. Level 2, and the level 2 is the equivalent of level 3 in the CPU. Okay, so here it's 73 megabytes. So now if you compare these two numbers, it looks like the GPU has more cache. Well, the numbers are certainly higher. So 73 is definitely larger than 30. And if you add all of this together, all of the different levels, the GPU is still higher. Okay? However, and by the way, the context refers to the registers. So on the GPUs, the context is actually pretty large, but I'll get into that in a moment. So it looks like the cache is bigger on the GPU, right? But there's a difference. The GPU has much higher floating point throughput. So what I want you to do is think about a calculation here. I'm just going to draw random calculations. This is not doing anything in particular. All right, so that's like a data flow graph. The nodes, of course, are operations, and when an operation is complete, let me show this intelligently. It goes downstream. Okay, so it's not data flow that some of us still get excited about. It's just a data flow graph. Okay, so when we look at this, there are different ways of looking at this. One is a number of operations. So let's call NF. That's the number of floating point operations in this calculation. Another important number is the latency. Okay, so L is for latency, and that indicates time. So of course, the number of floating point operations is determined by the calculation. The latency is determined by the speed at which, or the time that each of these needs to compute, and the critical path. Okay? So also note that in this calculation, we have intermediate values here. So this is an intermediate value. This is an intermediate value. Furthermore, when something is read from memory, I'll write this as a load. Okay, this value might be used in several different places. So notice how something loaded from memory might be used in several different places. So when we look at this, the thing to pay attention to is intermediate storage. Okay, so intermediate storage is going to be anything that is not read from memory or written to memory. In particular, here we have a load. Now, there's going to be a certain amount of intermediate storage here. And the reason that that's important is because we're going to have to put it somewhere. Where? Well, if the computation is tight, it'll be in registers. And that's going to be related to the number of contexts. But look at this. We have a load, and we use a loaded value in several places. That might be read from a cache several times. So we also need cache for that. Okay? So there's a certain amount of storage that's needed for this. So when we compare these two devices, we notice that how much of this storage is really needed. So to see how much storage is really needed, let's take that L. That's the amount of time, the latency for the calculation. And let's let theta fp be the floating point bandwidth. So that's floating point bandwidth, operations per unit time. Now, if we multiply theta fp times L, what we are going to get is the amount of computation done. Now, the number of floating point operations that can be done while this thing is computed. Okay, now let's divide this by NFP. Remember NFP down here? NFP is the number of operations needed for one computation. So if this is the number of operations that can be done during this calculation. So we get this. This is a number. And what's significant here is if you compare the CPU with the GPU, you're going to find that this is 25 times higher based upon our two sample devices. The latencies are not going to be very different. After all, multiplication units are not that different. Both Intel and NVIDIA and everyone else that's making them are going to use the best techniques to make floating point units. So latency is not going to be very different. But this is 25 times higher. This, of course, is the same for both of them. So what that means is you're going to have 25 times more of these operations in flight, overlapping, on a GPU than you would have in the CPU. Okay? So the significance here is that you are going to need 25 times more of this storage for intermediate values. Now, if the operations are close together, these will be in registers. And that will be OK because we have a lot more context. But consider something that's loaded from memory and reused. That's going to sit in the cache. There might be a significant difference, or it might have to go between multiple threads. So we need 25 times more storage for intermediate values. But if you look at the differences here, it looks like the GPU only has about twice as much. So the other burden on a programmer of a GPU is you've got to use your memory very efficiently. Okay? That means very careful management of your algorithm. The cache might seem like it's generous, but if you have all of those operations going on at the same time, it's not. It's actually about 10 times tighter than in a CPU. So that's the other important difference, a massive parallelism and the pressure on data. Now, in GPUs, the organization of the GPU also is, so in terms of memory, the organization of the GPU provides more options than a CPU. CPUs are very simple. You have two levels, global memory and registers, okay, and that's it. And if you're a programmer, then you know about global memory. The compiler cares about registers. You might dimly remember it. You just worry about memory. GPUs, on the other hand, have more options for storage. There is global memory and there are registers, but there are additional address spaces that are there and need to be exploited properly to make things go fast. So what's next here? All right, so this is a little diagram of a GPU. What I'll do is I'll describe that briefly, but then I'm going to get into the programming. Like, what do you need to do to program all of this? All right, so here's a diagram of one SM. Remember, it stands for symmetric multiprocessor. Let's start at the bottom. This FP32 is a functional unit, and in the NVIDIA devices, that will do a multiply add operation plus related operations like multiply and add. Importantly, it does not do division. Division is done somewhere else. So here we have the multiply FP32 units, and also there are integer units. The number of integer units maybe is half the number of floating point units. SF, that stands for special functional units. That's done for things like division and some other transcendental is exponential. Is there an exponential? I don't think so. But there is reciprocal square root, also approximate sine and cosine. By the way, the reason for having approximate sine and cosine is because it is used for graphics, and there, approximate is okay. Scientific computing, approximate is not okay. And in machine learning, super approximate is okay. All right, and loads and stores. All right, but let's get back to what we have here. Now, we said that in GPUs, there are lots and lots of threads. These threads are organized into a hierarchy. Now, at one level of the hierarchy, you have something called a warp. Now, if you know anything, you might have heard the term warp before if you know something about weaving or making textiles. So a warp is a group of threads that are held rigid. And you have a shuttle going back and forth, guiding another thread between them. That's how you weave. That's where the term warp comes from. So a warp is a group of threads. And in the NVIDIA devices, they kind of work as a team. Now, each thread, it operates in a way like a thread on a CPU in that it can do whatever the hell it wants. So that gives the programmers freedom. It allows you to port code that was written for the CPU and at least temporarily have all of the threads go their own merry way. But the hardware itself is going to treat the warp as a team. And I've used this in a class. So it's like you have a group of 32 friends, and it's time to go to lunch. If you all agree where to go to lunch, then you just go to that one place, like Panera. But suppose one set wants to go to Panera and the other set wants to go to the Union. So what you do in a GPU is first you go to Panera, then you go to the Union. Did I mention there were 32? What if each one of them wants to go to a different place? Then you're never going to finish lunch. It'll be dinner time by the time the last person eats. Okay, that's precisely the problem that happens in GPUs. Things are very slow. So those 32 threads have to work together. All right, so here's what's happening. A warp scheduler picks a warp to execute. And in the warp, there's an instruction. Hopefully, all of the threads agree on that instruction. If not, well, you got to pick an instruction from one of the threads. It executes. And then in each cycle, the warp scheduler is going to pick a warp. It'll dispatch the threads. Okay. So let me describe how to program it before I run out of time. So I'm going to go from slides to some code. So, and I'll also make this text larger. And I'll move this out of the way so I can see it. All right, so for this class, I'm going to start here. And so OpenMP, you've used it, right? Okay. And OpenMP, just for contrast, very simple. We tell it, we put a pragma there, and it parallelizes it. This is the ultimate. This is really convenient. So this is a loop. OMP parallel 4. It's going to parallelize this loop. Do the same thing here. Easy. C++, and of course you guys know C++, we have the thread library. Now when we're using thread library in C++, we need to write a function, an entry point for the thread. So here we write something called thread main. And when we create a thread, it's going to start by executing that. So I'm assuming that you've seen that somewhere. And here this thread is doing something simple. But here, within the thread, it's the thread's responsibility to figure out what to do. So the thread starts, and the idiom that we use a lot is compute the bounds on your work, a start and a stop. Then when you execute loops, use that start and stop. Okay? How is it computed? It's done using a thread ID. And here, since it's this is from the C++ library, so we simply declare, where is it? A vector, thread is in the C standard library. As soon as we call a constructor, here, when we call a constructor, we call it with the name of the procedure that holds a thread, and everything after it are arguments of the procedure. Since we wrote the procedure, we know what these arguments do, and it runs. Okay, so this is how threads are started on the CPU using the C++ library. There are other things like pthread and forks, but I'll describe it this way. So what's significant here is that we are creating threads one at a time. Yeah, it's in a loop, which is convenient, but each thread is individually created. Okay? And later on, for each thread, we need to individually wait for it to finish. Now, yes, we can do this in a more sophisticated way. Here, we're simply sequentially waiting for our threads to finish. But the important point here is that each thread is different and special and an individual, at least as far as creation goes. GPUs are different. The idea here is, first of all, because threads are managed in warps, you need to create at least the threads in bunches so the warps are created together. Furthermore, we have many separate SMs. So there's domains where each SM has its own L1 memory. So you need to somehow create threads in units where at least the threads within this unit are going to be able to share something. So that describes a hierarchy. So let's take a look at a very simple CUDA example. And first of all, a familiar part. Here again is a thread main. And like the C++ standard library in CUDA, you will write a thread entry point procedure. In CUDA, it needs to be preceded with the keyword global. Global indicates that it's the entry point for a thread. Okay, you can have arguments here. These threadIndex.x and blockIndex.x, these work as a thread ID. So you might think of a thread ID as being an integer from 0 to some maximum. In CUDA, it's actually a 6-dimensional vector. Okay, so it's kind of like your address. You know, you live on a street, in a town, in a country, you know, like that. So it's not really complicated, but it's there. The two important distinctions, though, are between what's called the thread index and the block index. The block index basically describes what sharing domain you're in. So if two threads have the same block index, they can share data. Now, there is another higher level of sharing, but I'm not going to get into that now. So if two threads have the same block index, it's easier for them to share data. If they both have, say, block index 5, then clearly their thread index will be different. All right, so here, thread main, and here it's doing computation. And in this case, it's operating only on a single data element. Over here, I'm computing a thread ID. And you notice that I'm operating on just one array element. So for the other example, there was a loop. Here, there's no loop. Now, this is not the best way to program in CUDA, but it works. And the reason is thread creation overhead in CUDA is much, much smaller. So small that in some cases, people, when they show you how to program, tell you to just launch one thread per data element. This would be unthinkable on a CPU. Nevertheless, it's still not a good idea. All right, so how are these threads created? And here is the equivalent. First of all, this line here is what's called a kernel launch, and this is where the threads are created and launched. So the actual file we're looking at, I know it looks like C++, but it's actually CUDA-C. So CUDA-C is like C++. It's compatible right now with C++20. So they've been keeping up. This is like one generation behind. But here, this is syntax specific to CUDA-C. So the 3 angle brackets indicate a kernel launch. This is the name of the routine you're launching. These are the arguments. You wrote thread main. You know what those mean. CUDA doesn't interpret them. But these 2 numbers, which I will emphasize here, are important. So this DG is the number of blocks. So threads within a block can share. dB is the number of threads within a block. So the total number of thread are the products of those 2 numbers. Okay? Now there's other things that I'm showing here. I'll briefly go over them, then I'll cover some more details. Memory. So the GPU can be used in several scenarios. In less expensive devices, like for integrated GPUs, on the same motherboard, they'll share the same global memory as a CPU. But for devices, oh, it's not here anymore, using HBM, that obviously can't be. So for discrete GPUs, they are going to have their own memory, not just their own address space, but their own device memory. Okay, so management of that memory is done through NVIDIA API calls. So this CUDA malloc is used to allocate memory on the device. This is the size of the array. This is the number of characters or bytes you wish to allocate. And that is going to be a pointer of where to write the starting address. So here we're writing 3 different addresses, X, A, and B. Those are memory addresses in the device address space. Okay? Not on the CPU. These addresses here are then passed as arguments to our thread main. Thread main here then uses A, B, and X in its calculation. So this is valid on the GPU. Try to do it on the CPU, you're probably going to get a segmentation fault. Okay. What other? So this is part of the CUDA runtime library. There's also a copy routine, and this is used to copy data. You can copy to the GPU or from the GPU. First argument is the destination pointer. Second argument is the source pointer. And the last amount of data and also the direction. So you could use this to copy both ways. All right, so that's a super simple example. Let me just show a few more go through some. Let's see. Another example here with some more details. All right, so CUDA is a system for programming. So here are the components of CUDA. The language is called CUDA-C. And as I said before, it's really, right now it's C++20. The routines that you call on the CPU, like CUDA malloc and CUDA mem copy, are parts of the CUDA runtime API. There's something else called the CUDA device API, which is very similar to the runtime API, but it's a little bit lower level, okay? But it does similar stuff. Now, CUDA, with the CUDA package, there is a tool chain. So you use NVCC as a compiler driver. So when you want to compile, you use NVCC. And the arguments are a lot like GCC or other compilers. You can put optimization options and so forth. And what it's going to do, it'll take your code. It's going to split it up into CPU portions and GPU portions. The CPU portions, it's going to pass off to the host compiler. So on the Linux, it'll be GCC. And stuff that needs to run on the GPU, it'll compile it. Now, obviously, to use this, you need a CUDA-compatible GPU. Let's see, what about CUDA-C? Blah, 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 blah. Runtime API. So things you can do with the API is move data and launch threads. Now, address spaces. This is something that I have the complete list in another one. So all right, so here's another entry point. And let's see. This is not that much different. Does a little more. I'm going to go to the next set here. This is a kernel launch. All right, compute capabilities. All right, now the GPUs have been evolving quickly. I mean, CPUs, yes, you get new CPUs every year or so, but the GPUs are evolving in a very significant way where some things no longer work or become very inefficient. Examples are L1 caches. Originally they weren't one, then they appeared for one generation, then they disappeared, now they're back. We have new features. Tensor cores are a few years old. In the graphics world, there is ray tracing cores and so on. So to keep all of this straight, there is a designation called a compute capability that describes the programmer visible roughly features. So the initial one was one called Tesla, and that test name is thoroughly obsolete, and it has nothing to do with the line of GPUs. So let's kind of scroll ahead. So we are roughly around here. So right now, these three devices are the ones that are out there. So if you go into Best Buy and you're not lucky, you get an Ada. If you are, maybe you'll get a Blackwell. Not the 10.0. The 10.0 is the data center grade ones. The B100s, which, you know, you get this massive thing with two B100 chips on it. If you have to ask, you can't afford it. Hopper is the older one. We have one here. And Ada, that's the RTX 4090, is implementing Ada. So I've also listed some basic features here. So Turing introduced, for example, ray tracing support. That's a graphics thing. Potentially could be used for things like tree searches. Sparse matrix support was given in the Ampere. I should say this crowd, definitely. Structured sparse matrix. Don't get excited. So here, when I say structured sparse matrix, the sparsity has to be very evenly spread out. It's not like, when you think of sparse matrices, you think of all kinds of crazy patterns where the number of non-zeros is like 95%, it's like 1 or 2%. Anyway, so machine learning support with the tensor cores. Also, very interesting data. Well, machine learning support started earlier here with the tensor cores. So for machine learning support, one of the things that they did was multiply add's important in machine learning. But in machine learning, precision can be a lot lower. So the multiplies would typically be done in a lower precision, the add in a higher precision. So that lower precision is started off being 16 bits, but you would add in 32-bit precision. Okay, so this is done by the tensor cores. But what has happened is precision has been shrinking, going down and down. Okay, so when these things go on, so one of the, in 8.9, official support for 8-bit floating point. Okay, so if that sounds crazy, but they've done it. So the way this works is the designation here for the two types, the exponent 4 bits, mantissa 3 bits. Okay, so that's 7 plus 1 for the sign. Or if you want a wider dynamic range, 5 bits of exponent, 2 bits mantissa. Okay, and in the latest devices, 4 bits. And you know, people have also talked about 1 and 2 bits. So there's a lot of experimentation here on really driving down the precision, and the reason is because there are a massive amount of weights. Okay, let's see. All right, let me talk more about the devices themselves instead of going through their history, so we save time. Kernel launch I described. So I'll just remind you, unlike in a CPU, we create threads one at a time. In a GPU, we create them en masse once, and we specify the launch configuration, number of blocks and the number of threads per block. Here it's done as 2 dimensions, and they said that there were 6 dimensions. You can actually provide 6 dimensions. Now, why 6 dimensions? Well, 6 is 2 sets of 3. A lot of the uses of this is scientific computation, where you might be doing some kind of structured grid computations that models a physical object, heat through a part, or the atmosphere, flow of air and so forth through the atmosphere, and those are all in 3D space. So the thread ID, the thread index, could have 3 components, x, y, and z, which you could map on to physical Cartesian coordinates. That's the idea. So that's done as a convenience. If you know something about programming, you might be suspecting, oh, optimization. And I thought that too, but NVIDIA specifically says, no, no, it's just a convenience. All right, so when we do this launch, most people are going to do 2 numbers here, number of blocks, threads per block, but if you want, you can do 6 dimensions. Now, when you do the launch, the number of blocks must be, if you want to use your hardware, it should be a multiple of the number of SMs. Okay? So if you have 128 SMs and you launch 1 block, then you are making use of 1/128th. And if you have 128 SMs and you launch 129 blocks, then you are highly imbalancing things because one of those SMs has twice as much work to do as the other. And if you're waiting for everyone to finish, it's not a good thing to do. Okay, so the best practice, the default, is to make the number of blocks an integer multiple of the number of SMs. Okay? What else? All right, so the organization. We talked about this organization, and I know it could be confusing. So the warp is used internally by the hardware, and that's one of the reasons they can cut down on a lot of the cost, because even though at each clock cycle, each SM effectively can start 128 different threads, they're managed in warps. So we have 4 schedulers. Each scheduler is managing a warp. And when it picks a warp, it's going to pick an instruction for one of the threads. Hopefully they're all converged, so it's one instruction. So the effort of fetching, decoding the instruction, checking for dependencies and so forth, is done once on behalf of up to 32 threads. In contrast, if you had a 32-way superscalar processor, then each context would have its own program counter and there'd be no special sharing. You'd have to decode 32 separate instructions and with all the complexity that goes with it. So here the savings is 1/32. Okay, so that's a warp. We know what a thread is. So a block is a grouping of threads, and the threads within a block can share. A block is assigned to a GPU. To an SM. A block cannot be split between 2 SMs. It has to go on one. Now, there's also something called block clusters. I kind of hinted at that earlier. If 2 blocks are in the same cluster, then they will be assigned to the same CPU, to the same SM, and they will be active at the same time. If 2 blocks are not in the same cluster, they may or may not be assigned to the same SM. And even if they are assigned to the same SM, it's possible one block runs and finishes before that second block starts. So within a block cluster, not only are the different blocks in the cluster assigned to the same SM, they run at the same time, and this enables sharing. Okay? Grid refers to the collection of blocks. Okay, hardware organization, we've talked about this. So streaming multiprocessor is a generic name. I'll call it an SM. Sometimes NVIDIA calls it an SMX. And it's also sometimes called an MP. So don't get confused. Functional unit. We talked about the functional units here. So FP32 is sometimes called the CUDA core. And it does addition, subtraction, multiply, fuse, multiply, add. There are also FP64 functional units. So if you get a data center grade, like an H100, the number of FP64s is half the number of FP32s. If you buy the consumer version, then you are going to get very few FP64s. It's not going to be 1/2. So I checked. I didn't realize it was this bad. In the current generation, the number of FP64s is equal. An FP64 is shared amongst 2 schedulers, meaning 128 floating point 32s, 2 FP64s. Okay, why do they do this? Well, some people here might be familiar with CCT. Find someone who's done scientific programming and tell them to port their 64-bit code to 32-bit code. What kind of expression will they have on their face? Okay, so they're serious about this stubbornness. So if they have to pay 10 times as much for their computing device, they'll pay it rather than port. That's why there's only 2 on the consumer grant versions. All right, also N32, special functional unit, as I said, does reciprocal square root, and some trigonometry. Load stores for accessing memory. Tensor cores, what these do are matrix operations. Now, there's not a single matrix multiplication. They're done in pieces. But what makes the tensor core special is that unlike the other operations, when you operate a tensor core instruction, you definitely are having all the threads in a warp participate. So the data for a matrix comes from all of the threads in the warp, in contrast to other instructions where it's individual to a thread. Let's see here. I can't go through everything here. I want to talk about the address spaces. And all right, so global data, like a CPU, it could be an off-chip memory, HBM, level 2 cache, and the read-only cache is something which is in older devices used for the textures. L1 cache local to a core, and I'm not going to go through this. All right, the address spaces are on the next one. And that's definitely important enough that I'm going to skip ahead. All right, so address spaces. Okay, so when we talk about GPUs, there is a global address space, which works like regular memory. There is something called the constant address space. Now, and there is a shared address space. There's also something called local, but shared address space is what I want to talk about now. So each GPU, each SM has a piece of device memory which can be used for one of 2 purposes, or maybe 3. L1 cache, or the shared address, or the shared address space. So we have this device memory, and so here we have an SM. So we have this, I'll call it high-speed mem. I'll just show it like this. L1 cache, and see this line? This can actually be moved. So there's a certain size here. It might be 64 KB, 100 KB. And it's divided between the L1 cache, and by the way, in the computer architecture world, we are not beneath using a $ to indicate an abbreviation for cache. We're not above it. Or shared memory. So the shared memory will be in this storage. So shared memory and cache, in terms of how fast you can access it and capacity, are similar. What's the difference? Cache is automatic. When you access data, if it hits the cache, you get it quickly. If it's not in the cache, then we go to the next layer in the memory system, retrieve the data, put it in the cache. So next time you access that same address, you'll get the data quickly. That's how the cache works. And that is fairly effective. but it's not perfect. And remember how I said that it might look like there's more memory on the GPU, but actually, if you compare it in terms of how much floating point there is, it's a lot less. So the methods used to decide what gets replaced from the cache when you bring something new in might not work for you. So the typical method is least recently used, which is fairly effective, but it sometimes will evict data that you need. So it might be better to manage your own storage. And for that reason, there's shared memory. So with shared memory, you essentially explicitly move stuff in there. Okay? And when you move stuff in there, if you're overwriting something old, well, you know what you're doing. You're not going to overwrite data that you'll need. So there is a separate shared address space that will share the memory here. By the way it works is when you set things up, you can specify the dividing point if you wish. But simply by using shared memory, you're going to occupy this. You can also dynamically allocate it, which is why you might need to specify in advance your request. Okay, by the way, two different concepts, shared memory, shared address space. The shared address space refers to the range of valid addresses. Shared memory is what's written here. All right, so to declare shared memory, use the keyword shared and follow that by any data type you want. I'm showing two examples here. Ordinary integer. Here we have an array, and by the way, float4 is a data type used in CUDA. Now, I've talked about the fact that CUDA's origins is in graphics. Not CUDA, GPU's origins is in graphics. In graphics, one operation which is done all the time is multiplying a 4-element vector by a 4x4 matrix. The 4-element vector is used to represent a Cartesian coordinate. And I know it's something called homogeneous coordinates. Also used sometimes for color transformations. So these are very frequently done operations, which is why you'll see the float4s are there. Okay. Let's see. I'm trying to think of what I want to cover here. Let me go back to that other set. And at some point, yeah, I have an idea. What do you guys want to see? I can show you all kinds of stuff. Anything in particular? Now, if you're taking one of my courses, that's not fair, because you could ask in class tomorrow. So.
The functions for exponential and logarithmic functions are considered special functions here?
I don't think they, so what, do they have exponential? Yeah, it would be special functional unit, but there's reciprocal square root, and there are trigonometric operations. So those would be in the special functional unit. Any other questions? What time? So the class is officially over now? Okay, so any other questions?
Can you share the slides or? Yeah, that's very important.
Yeah, I mean, I could, yeah, sure. Well, I'll give that to Hartmut, I mean, however you want to do it. Right, and those slides actually go on. So it's actually based on a set from a course. So if you go after that, it's going to go through all kinds of different computing devices. So, okay, all right. Well, thank you for.